But nowadays almost everywhere we see electric locomotive because of the electrification of the track. Majority of the tracks have been electrified. So, we see primarily electric locomotive. In electric locomotive, the power is supplied from the overhead line through a line which is called a catenary line. So, we will see how the power is being supplied. So, we have the catenary cables like this, and we have this is the catenary line which is called the catenary cable, and then we have a contact wire with which the locomotive makes contact. This is called the contact wire. The contact wire is kept almost horizontal by the dropper wires. So, these are the dropper wires. So, we have the droppers here. And the contact wire should be horizontal, and the inclination of contact wire should be less than 1 in 300. So, this has to be absolutely horizontal. So, the catenary wire basically gives it a mechanical support, and the contact wire is kept horizontal by dropper wires which are connected to the catenary cable. Now, the train or the locomotive makes contact with the contact wire through an equipment called pantograph. So, we have a pantograph or a pantograph collector. So, this is a pantograph collector. It is something like a pentagon. This is a pantograph collector. Pantograph collector. So, this this is a collector strip, and this is the contact wire. And the contact wire is not at a particular position, it is staggered to even out the wear of the contact strips. It is staggered as the train moves, the contact wire is also staggered, so that the wear of the contact strip is almost even. So, this is how the current is collected, and the rating of the drive, when we talk about the rating of the traction drive, is as high as can be 6000 HP, which means approximately 4.5 megawatt or more. So, we are talking about a drive which is a high power drive, and this power is not supplied by a single motor. This power is supplied by a combination of motors, maybe 4, 6 and so on. So, these motors, they drive the axles are connected to the wheels. So, let us see how the motors drive the axles. So, we have the axles here, these are the wheels, and we have the axle, and each axle is connected to 2 wheels. These are the wheels, and they run on predefined track. So, we have the track here on which the train runs, and the motor usually sits on the axle. So, we have the motor here, it basically sits on the axle. Each axle has got one motor, and then we have a gear arrangement. We have a gear here, and then we have a gear in the axle. So, these are the fixed gears in this case. So, this gear is connected to the axle, and as the motor rotates, the gear also rotates, and hence the wheel rotates. So, this is the motor which is mounted on the axle, and we have the gears. The gear is driven by the motor, and the axle rotates, and hence the wheel rotates. So, what about the nature of the traction load? We will now discuss about the nature of the traction load. Now, if we see the nature of the traction load consists of various components. Typically, the variation of the load with speed looks like this. So, if we see the variation of traction load with speed, so this is the speed in this case, and we have the traction load. So, this is called the train resistance. So, this looks like this. So, we have the various component. F1 is called the internal friction, which is with the bearing, guides, etc. F2 is called the external friction, which is the wheel flanges and rail, and F3 is the air friction. So, the train resistance Fr is given by F1 plus F2 plus F3. So, when the train is moving, we have internal friction. The internal friction are with bearings, etc. And we also have external friction. The external friction is with the wheel and the track. And then we also have air friction, because the train is moving at certain velocity, and it is basically facing the air. So, the air is also offering a resistance for the movement. So, primarily these are three components: the internal friction, external friction, and the air friction. In addition to that, there is a gravitational force which may be acting if the track is having some gradient. If the track is absolutely horizontal, there is no gradient force, but however, sometimes when the locomotive is moving in an hilly area, there may be a up gradient or there may be a down gradient. Depending upon the gradient of the track, there would be a gravitational force. So, in addition, the gravitational force comes into picture. The gravitational force comes into picture in case of a gradient. So, in case of a gradient, there will be a gravitational force. Now, this is basically we are plotting here the steady state behavior. We are plotting here the steady state. Behavior. Now, there is an important parameter which is associated with traction. When the wheel is running on the track, there has to be an adhesion between the track and the wheel. unless there is adhesion, the train cannot move forward. Because there is adhesion, when the wheel is rotated by the motor, the train moves forward. The adhesion can be said in a crude word like a friction, but in electric traction we call this to be adhesion, and we have a parameter called coefficient of adhesion. Let us see what is coefficient of adhesion. So, we have coefficient of adhesion, which is called Ca. So, what is this coefficient of adhesion? The definition is the maximum tractive effort that can be applied without slipping of the wheel, without slipping of the wheel, divided by the weight on the driving wheel, on the driving wheel. So, we have the wheel which is resting on a track, and the wheel is basically connected to another wheel through an axle, this also another track. So, we have some weight on this wheel, some weight is there here. So, we have some mass, and m into g is the weight. So, we have m into g, and this weight is distributed between these two wheels, and when the wheel is rotating, it has to move forward. So, the definition of coefficient of adhesion is that maximum tractive effort that can be applied without slipping of the wheel. The tractive effort is the force which can be applied here without slipping of the wheel, divided by weight on the driving wheel. So, the tractive effort is being applied by the motor. The motor is producing a torque, and the torque by the radius of the wheel is the tractive effort. So, the tractive effort is F t, which is the torque divided by the radius. So, we are applying a tractive effort, so that the vehicle moves forward, this is F t, and if the tractive effort is more, the wheel may start slipping, and if the wheel slips on the track, there will be burning of the track, there will be wear and tear of the track and the wheel. The wheel will be damaged, the track will also be damaged, because the wheel rotates at a high speed and it is slipping on the track. So, the track will be worn out. So, to prevent that, we have to ensure that the tractive effort which is applied is less than the permissible value, and that is decided by the coefficient of adhesion. The coefficient of adhesion is defined here. Now, this depends upon various parameters. The coefficient of adhesion depends on number 1, type and condition of surfaces, at the point of contact. So, when there is a contact, the contact here, the coefficient of adhesion depends on the type and condition of surfaces at the point of contact. So, we have contact here and contact here. So, it means the presence of oil, whether there is presence of oil, grease, these will reduce the coefficient of adhesion. Water, the presence of water on the track will also reduce the coefficient of adhesion. The presence of snow will also reduce the coefficient of adhesion, and so on. So, if we are having the train on a rainy day, the coefficient of adhesion will be less. If the track has got oil or the track has got grease, it becomes slippery. The coefficient of adhesion, which is something very close to the coefficient of friction, that becomes also less. So, the condition of the track and the wheel determine coefficient of adhesion. Furthermore, the coefficient of adhesion also depends on the vehicle speed. Vehicle speed. If the vehicle speed is high, the coefficient of adhesion is less. If the vehicle speed is low, the coefficient of adhesion is more. So, if we plot actually graph between the vehicle speed, V is the speed of the vehicle, versus the coefficient of adhesion, it will basically look like this. So, which means at high speed the coefficient of adhesion is less. So, at low speed the coefficient of adhesion is more. So, high speed means speed indicates low CA, low speed indicates relatively higher CA. So, if the speed is low, the coefficient of adhesion is high. So, this is how the coefficient of adhesion varies with the vehicle speed. It also depends on the other parameters like nature of the torque speed characteristic, nature of the torque speed characteristic, so let us say that we have two types of motor. One is a motor with the speed and the torque. The speed regulation is not very small. So, the speed is only dropping gradually. This is basically a separately excited motor, separately excited DC motor. And we also have another motor where the speed torque characteristic is not that stiff, something like this. We have a series motor, let us say, series DC motor. Now, in this case, in the first case, when we have a separately excited DC motor, if the wheel slips, the torque reduces very quickly. So, when the torque reduces quickly, the wheel regain the grip on the track. So, this will have a higher coefficient of adhesion. So, here for a small change in the speed, when there is a wheel slip, the speed increases, but the torque change is quite significant. The torque change is quite significant. When there is a wheel slip here, suppose it was operating at this point and the wheel is slipping, so the speed will increase to say from point A to point B. So, when it increases to point B, the torque decreases from Ta to Tb. So, when the torque decreases, the tractive effort also decreases. So, the wheel regains its hold on the track and the wheel slippage is prevented. So, this has got higher coefficient of adhesion, but on the other hand, if we have a series motor, if there is a wheel slippage, the speed increases from, let us say, from A to B, but the relatively the decrease in the torque is not that high compared to shunt or separately excited DC motor. For a series motor, the coefficient of adhesion is less. So, this has got high Ca and this will lead to a low Ca if you go for a DC series motor as a traction motor. And we have another factor which also determines Ca, which is the motor connection. Motor connection. If the motors are connected in series, series connection will lead to a low CA, and parallel connection will lead to higher CA. Because when the motors are in series, if there is a wheel slip, the back EMF will increase, the current reduces for all the motors. The motors corresponding to a wheel which was not slipping also will have a reduced torque. So, the series connection will have a low CA because all motors are affected, but in a parallel connection only that motor which is slipping will have reduced torque. So, we have relatively higher attractive effort. So, we have a higher CA here. So, this is about the coefficient of adhesion. Now, we will now understand the duty cycle of the traction drive. When the traction drive is or a locomotive is moving from one station to the other station, how does the speed changes, how does the torque changes? We will be discussing that right now. So, we have the duty cycle of traction drive. Let us say that a locomotive is moving from one station to the other station. It starts, it accelerates, it reaches the maximum speed, then before it reaches the next station, it has to brake and come to a standstill. So, the typical speed variation is as follows. So, if we see the speed variation here, so the variation of the speed is of this sort, we are plotting against time. So, initially the speed remains, the speed is changing here, this is the speed, and we have a linear change in the speed from 0 onwards, x axis is the time axis, and this is the constant torque. Then we have constant power, then we have the free running period, then before the stop the motor is switched off. So, we have the coasting period and then we have the braking period. So, it something looks like a trapezoid. So, the first part where the speed is almost constant, this is called constant torque up to this point T1, let us say, and from T1 to T2 the power remains constant. So, we call this to be constant power region. So, the speed has reached the maximum possible value and then it runs freely, and we call this to be a free running period, free running here. And then we have something called the coasting period. Coasting means the motor is switched off, the power is switched off. So, this is also called the power off period. And then we have the braking period. So, we have T1 0 to T1 is a constant torque, T1 to T2 is a constant power, T2 to T3 is a free running period, and T3 to T4 is the coasting period, and T4 to T5 is the braking period. So, if we see the torque variation here, how does the torque change? From 0 to T1, the torque almost remains constant at the maximum possible value. So, this is the torque. And then from T1 to T2, torque decreases, but the power remains constant. and here we have reached the maximum possible speed, then we only supply the frictional torque and the air resistance, which is very small, and from T3 to T4 the engine is or the motor is switched off. So, we have 0 torque absolutely, and then from T4 to T5 the motor is braked. So, we apply a negative torque for the braking. So, the torque changes as follows. Now, if we see the power variation with respect to time, let us see how does the power changes with time. So, initially the motor are being powered. So, the power gradually increases and we reach the maximum possible power, that is the rated power, and then we operate at maximum power, and then during the free running period the power decreases to minimum value, and then when the motor is switched off the power is 0 here, and then when we are braking the torque is negative. So, power also become negative because the power is fed back to the supply, and when the gradually the speed comes down to 0 the power becomes equal to 0. So, this is the variation of the speed, the torque and the power for the motor, but we are assuming that there is no gravitational force. So, these plots are actually for a level track. When the track is level, there is no gradient, the track is absolutely horizontal. So, these are the plots for level track, for leveled track. It means the track is absolutely horizontal. Horizontal track. Now, if we want to find out the distance covered, the distance covered is basically the area under this curve. So, we have to find out the distance. So, if you want to find out the distance traveled by the train, we have to find out the area under this curve. So, let us see how we find out the distance. So, distance travelled is equal to the area under the speed time curve. So, if we take the speed time curve, which is this curve, and if we calculate the area under this curve, we get the distance travelled. Now, we will just try to do the calculation of the drive rating and energy consumption. Calculation of drive rating and energy consumption. So, we will redraw our speed torque, I mean the speed versus time diagram. This is our speed in the y axis. So, we have constant torque, constant power, free running period, coasting period and braking period. So, these are the various period we have, and we will find out first of all the distance covered, and also we will find out the drive rating. So, we have understood how a train moves from one station to the other station. It goes through the various modes like constant torque, constant power, free running period, coasting and braking. So, the subsequent calculation of the distance and the drive rating we will take up in the next lecture.